So now we're going to take a look at estimating a population proportion P. Okay, so the point estimate that we would use for the population proportion P is the sample proportion P hat. And that means we're going to collect a sample. We're going to make a sampling distribution. We're going to have a bunch of samples of size n. That's our fixed number of trials because this has to be binomial. So there is a fixed number of trials. There is a probability of a success or probability of meeting a certain criteria, which is the population proportion P. That population proportion is independent from trial to trial. And that doesn't change from trial to trial. So this is binomial. What we're going to do is we're going to actually collect a whole bunch of samples of size n and calculate the sample proportion p hat and use that as a point estimate for the population proportion. So we collect one sample of size n and calculate the sample proportion p hat. That's our point estimate for p. Notice it's an overestimate of p. We do it again, a sample of size n, and calculate the sample proportion p hat. That one underestimates p. We do it again. We get another overestimate, slightly better estimate though. Sample of size n, calculate the sample proportion. And we keep doing this. We keep getting a bunch of sample proportions. We just keep collecting samples of size n and getting sample proportions. And you notice that all these sample proportions are kind of piling up right above the population proportion, and they're roughly bell-shaped, right? Well, it turns out that this is the case for sample proportions. Sample proportions are normally distributed, and the mean of that sampling distribution of sample proportions is actually the population proportion. So it turns out that the mean of the sample proportions is equal to the population proportion, and that is roughly normally distributed. Okay, that means since it's roughly normally distributed, we should be able to use z-scores to find probabilities for certain sample proportions. So if you have a specific sample proportion, we can use a z-score to calculate what the probability is of getting that particular sample. In order to do that, we have to kind of modify the formula that we have for z-score. And the way that we would modify it is to remember the fact that when you're dealing with a binomial distribution, the mean, mu, is actually equal to n times p, and the standard deviation, sigma, is actually equal to the square root of n times p times q. So mu is n times p for the binomial, so this mu could be equal to n times p, and sigma is equal to the square root of n times p times q, this down here. You get this, and well, you can go ahead and you can divide everything by n to create an equivalent expression. If you divide everything by n, multiplying the top and bottom by 1 over n, you get this. And x over n is actually equal to p hat. P hat is x over n. That's the sample proportion. So we can change this x over n here into a p hat, and we get this formula. P hat, which is x over n. Remember, x over n is p hat. And then the n's would cancel here, leaving just p, and the n's would cancel here, leaving you the square root of p times q over n. All right, so this is the z-score formula for calculating probabilities for the sampling distribution of proportions. All right, so notice that the top of this is e p hat minus p. It's the point estimate p hat minus the population parameter p. So it's taking a point estimate and subtract. It's the distance from any particular value of p hat to p. E, the margin of error, is the distance from p hat to p. All right. So I'm just going to change the numerator here from p hat minus p to e, the margin of error. And then I'm going to multiply both sides by the radical here, the square root of pq over n, to get this formula. This is my margin of error. Remember, the margin of error is just the distance from any particular value of p hat It's that distance from that particular value to P, all the way to P. So that's the margin of error. The margin of error is just that distance, okay? So since this is related to a z-score, that means that the sampling distribution can be approximated by a z-distribution, the standard normal distribution. So if I want to find probabilities for my sampling distribution, I can find probabilities for the z-distribution, the standard normal distribution, and use those probabilities instead uh, as replacements here, all right? Now, the problem is, in order to calculate E here, the margin of error, I would need to know P hat and Q. So I'm just going to use, well, let me rephrase that. In order to find E, I need to know P and Q, the population proportion and the complement, 1 minus the population proportion, which is Q. Well, that's not known. We're estimating it actually. So instead of using P and Q, we're going to estimate P and Q with P hat and Q hat. So P hat is the sample proportion and Q hat is 1 minus P hat. Okay? So let's take a look at an example. A poll of 49 voters. So 49 voters is our sample. We have a sample size of 49, found at 57%. So 57%. So I know that n is equal to 49. I know that n is 49. And I also know that p hat, it says 57% favor Donald Trump. So p hat is 0.57. So that means I also know q hat. Q hat is 0.43, which is 1 minus 0.57. So here I know I have 49 for n, I have Q hat is 0.43, and I have P hat is 0.57. I have everything I need for the radical. The only other thing I need to calculate E would be the Z here, Z. Well, that's where this 95% comes in. You see that 95% is your confidence level, and your confidence level then is 0.95. What you need to do is you need to calculate the significance level alpha, and alpha is 1 minus the confidence level. And in this case, that's 1 minus 0.95 or 0.05. 0.05. When you're doing a confidence interval, what you want to do is you want to take this significance level, 0.05, and you want to split it up so that you have half of it in the upper tail of your Z table, of your Z, and half of it in the lower tail with a Z-score down here to represent that. So basically, 0.05, half of it needs to be up here. So up here, I'm actually looking for half of 0.05. Half of 0.05 is 0.025. So half of 0.05 is 0.025. 0.025. And I need the other half to be back here. 0.025. So what that means is I'm looking for the z-score that separates the top 2.5% from the bottom 97.5%. So I need 2.5% in the upper tail. 2.5% in the upper tail. So I come down here and I'm going to look inside the areas here. I'm going to look for the areas here. And you notice this table gives me the upper tail. This table that I'm looking at gives me the upper tail. Some tables give you the lower tail. This particular table gives you the upper tail. So in the upper tail, I want 0.025. So I look for the closest number to 0.025, and I identify it. It's exactly 0.0250, 0.025. Now I need to find out what the z-score is that has 0.025 in the upper tail. That z-score is the sum of this, 1.9, and zero point zero 0.06. So the z-score that I need then, the z-score that I need is 1.96, 1.96, because that z-score separates an upper tail area of 0.025. So I can go back to my problem here, and I say that I need the z-score to be 1.96 because that separates this upper tail area here of 0.025, and that's exactly what I need to calculate the margin of error here, to calculate the margin of error. Okay, remember the margin of error is the distance between any given value of p hat and the population proportion p. So basically, if I graph my value for p hat, which is 0.57, the margin of error is going to be the distance between that p hat and the actual p. So let's see here. Um, I'm going to calculate that margin of error. The margin of error then, E, it says here is equal to Z, which I just found out to be 1.96, multiplied by the square root of P hat. P hat is 0.57, so 0.57 times Q hat, which is 1 minus P hat, which is 0.43, all divided by n, which is in this case 49. And when you do this, you get that E is approximately, when you round it, approximately equal to 0.14. So the margin of error is approximately 0.14. So now let's assume that 0.57 is an overestimate of the actual population proportion like this, okay? Well, I want 2.5%, 2.5% to be the probability that I overestimated way too much, So I want 0.025 in this upper tail. And that means that the margin of error, if I want 2.5 up here, remember I used 1.96 here, which separated 2.5 in the upper tail. That means the margin of error then separates that 2.5% in the upper tail, and it would capture P, if I overestimated, it would actually capture the true population proportion 97.5% of the time. If I had an overestimate, it would only miss P 2.5% of the time. So that means that the lower limit in my confidence interval is 0.57, which is P hat minus E, which is 0.014. So that's going to be P hat, which is 0.57 minus 0.14, which is my E, 0.14, and I get 0.43. So the lowest value that I want to use as an estimate for P is 0.43. And then I'm going to do the same thing. Well, suppose that the P hat that I got, suppose that my P hat 0.57 is actually an underestimate of the true population parameter. Well, I want to make sure that I extend from p hat far enough that I would only be underestimating too low 2.5% of the time. So I want 0.025 down here too, so that I can get the right value for E here. And it turns out it's the same value because back here is negative 1.96 because of the symmetry of the graph, okay? Because of the symmetry. So in this case, I'm going to take 0.57 and I'm going to add to it the margin of error 0.14. And when I do that, 0.57 plus 0.14, I get 0.71. So I've separated in the middle here 95%. 95% of my p hats would be in the middle here. 95% of my p hats would be in the middle of 0.43 and 0.71. All right, so this procedure basically captures the true population proportion 95% of the time. It only leaves 2.5% if you overestimate it only leaves 2.5% above that. And if you underestimate it, it'll only leave 2.5% below that, meaning you will actually capture the true population proportion 95% of the time. So this is the final answer. This is the confidence interval estimate. I'm assuming that the true population or the true proportion of Trump supporters in the population is somewhere between 0.43 and 0.71%.